Time is not what you think it is. Not a river flowing in one direction, not a force that moves things forward, not even a dimension in the simple sense that the word usually implies. Time, as physicists understand it, is a property of space-time, a geometric feature of the universe that behaves differently depending on where you are, how fast you are moving, and how much mass surrounds you. And in certain places, real physical places that exist in the observable universe right now, the behavior of time becomes something that no human intuition can correctly anticipate. Not slower, not faster, something more fundamental than either. In the mathematics that describes the interior of a black hole, the dimension we experience as time becomes spatial. The dimension we experience as space becomes temporal. Inside the event horizon, what was a direction becomes a destiny. What was a moment becomes a location. The future is not ahead of you in the sense of a timeline extending forward. The future is a place you are moving toward not by choice, but by the same inexorable process by which time passes outside. And at the singularity, the end point of that journey, time, as we understand it, does not slow to a stop. It ends. What this means, what it actually means for the physics of reality, is not fully understood by anyone alive. But the mathematics is not ambiguous. In at least one class of physical objects, the relationship between time and space that every human nervous system takes for granted does not apply. Time, in those places, does not run backwards in the colloquial sense of effects preceding causes. It runs differently, in ways that the words we have for time were not built to describe. And those places are not hypothetical. They are out there, right now, in the darkness between the stars. Begin with what time actually is. Einstein's special relativity established in 1905 that time is not absolute. Two observers moving at different velocities experience time differently. The faster you move relative to another observer, the slower your clock runs relative to theirs. This is not an illusion. It is not a measurement artifact. It is a real physical difference in the rate at which time passes. The effect has been measured. Atomic clocks flown on aircraft tick slightly slower than identical clocks on the ground. The GPS satellites orbiting Earth carry clocks that must be corrected for relativistic time dilation. Without the correction, the accumulated error would make GPS navigation useless within hours. The physics is real, and it is in your phone. General relativity added gravity to the picture. Not only does motion affect the rate of time, so does mass. The deeper you sit in a gravitational field, the slower your clock runs relative to a clock further from the mass. A clock on Earth's surface ticks slightly slower than a clock in orbit. A clock near the surface of a neutron star ticks dramatically slower than a clock far away from it. This effect has also been measured directly. The Pound-Rebka experiment in 1959 detected the gravitational redshift of gamma rays traveling upward in Earth's gravitational field, a fractional frequency change so small it required extraordinary precision to measure, but real. These effects, time dilation from velocity, time dilation from gravity, are the familiar faces of relativistic time, measurable, confirmed, and incorporated into technologies that billions of people use daily without knowing it. But they are not the strange part. The strange part begins at the event horizon of a black hole. From outside a black hole, watching an object fall in, you would never see it cross the event horizon. Time dilation near the event horizon is so extreme that the infalling object appears to slow down asymptotically, moving more and more slowly, its light redshifting toward longer wavelengths, its image freezing at the boundary as time dilation approaches infinity. From the perspective of the infalling object, nothing unusual happens at the event horizon. The crossing is smooth, unremarkable, a boundary defined by geometry rather than by any physical surface or force. But inside the event horizon, something has changed that is more fundamental than the rate of time. In the mathematics of description of space-time outside a black hole, there is a clear distinction between space and time. Space is the set of directions you can move toward or away from. You can go north or south, toward the black hole or away from it. Time is the dimension along which you are carried regardless of choice. You cannot stop time, but you can orient yourself differently in space. Inside the event horizon, the mathematics swaps these roles. The coordinate pointing toward the singularity, previously a spatial coordinate, a direction you could in principle move toward or away from, becomes timelike. You cannot choose whether to move toward the singularity any more than you can choose to move toward the future. The singularity is not in front of you, it is in your future, unavoidable, unreachable by any change of trajectory. The coordinate that previously pointed along the time direction, the direction of increasing time, the direction you were being carried regardless of choice, becomes space-like. Inside the event horizon, what was time becomes a direction you can orient yourself along. You can move in the direction of increasing time or decreasing time in the spatial sense. This is where the language breaks down entirely. Because what does it mean to move in the direction of decreasing time? Not to reverse cause and effect, not to make broken eggs unbreak. Something more geometrical than that, and more disturbing. A freedom of orientation in a dimension that outside the event horizon permitted no freedom at all. There is a specific class of black hole where this becomes even stranger. Carl Schwarzschild solved Einstein's field equations for a non-rotating, uncharged black hole in 1916, within weeks of the publication of General Relativity, while Schwarzschild was serving on the Russian front in World War I. He died of illness shortly after. His solution describes the space-time geometry outside and inside a simple black hole. But most black holes in nature are not simple. They rotate. And rotating black holes, described by the Kerr solution, derived by Roy Kerr in 1963, have a space-time geometry that is dramatically more complex than the Schwarzschild case. A rotating black hole has not one, but two event horizons, an outer horizon and an inner horizon, and a region between them where something happens to time that has no analog in everyday experience. In the region between the outer and inner horizons of a Kerr black hole, the timelike and spacelike coordinates swap as they do in the Schwarzschild interior. The singularity is in your future. Standard features of the Schwarzschild interior apply, but cross the inner horizon, and the mathematics suggests this crossing may be survivable in principle, depending on how realistic the idealized Kerr solution is. You enter a region where the future is not uniquely determined by the past. There are closed time-like curves.
A closed time-like curve is a path through space-time that loops back on itself. A world line, the path of an object through space and time that returns to its own starting point. Not in space alone as a circular orbit does, in space-time. A path through both space and time that ends where and when it began. An object following a closed time-like curve would experience time normally along its path. Clocks would tick, events would occur in sequence, cause would precede effect locally. But at the end of the curve, the object would find itself at the same point in space-time from which it started. It would meet itself. This is not a science fiction construction. The Kerr solution, the mathematically exact description of a rotating black hole, contains closed time-like curves in the region near the ring singularity at its center. They arise naturally from the geometry of the rotating spacetime, not from any exotic physics introduced by hand. Whether they are physically real is a different question. The Kerr solution is an exact vacuum solution. It describes a rotating black hole in complete isolation, in an otherwise empty universe with perfect symmetry. Real black holes are not perfectly symmetric. They form by imperfect collapse. They accrete matter that disturbs the geometry. The interior of a real Kerr black hole almost certainly differs from the idealized mathematical solution in ways that may eliminate or modify the closed time-like curves. Stephen Hawking proposed the chronology protection conjecture, the hypothesis that the laws of physics conspire to prevent closed time-like curves from forming because their existence would allow causality violations that are inconsistent with quantum mechanics. The conjecture is not proven, it is not disproven. It is a hypothesis that many physicists find physically motivated and others find unjustified. The closed time-like curves in the Kerr solution may be artifacts of idealization, or they may be real features of rotating black hole interiors that we have not yet accessed with any observation. We do not know. Outside of black holes, there are regions of spacetime where time behaves in ways that deviate dramatically from the everyday. Near a neutron star, the collapsed remnant of a massive star containing more mass than the Sun compressed into a sphere 20 kilometers across, gravity is so intense that time dilation is measurable over distances of meters. A clock sitting 1 meter closer to a neutron star than another identical clock ticks measurably slower, not by a tiny fraction, by an amount that compounds rapidly as you approach the surface. At the surface of a neutron star, where the escape velocity is approximately half the speed of light, time dilation is severe enough that 1 second on the neutron star corresponds to approximately 1.5 seconds far from it. Processes that take 1 second on the neutron star appear to take 1.5 seconds when observed from a safe distance. The most extreme known neutron stars, millisecond pulsars rotating hundreds of times per second, combine extreme gravity with extreme rotational velocity, producing a time dilation environment that combines gravitational and special relativistic effects simultaneously. An observer on the surface of a millisecond pulsar, if such a thing were conceivable, would experience time running at a fraction of the rate experienced by an observer safely distant. An hour on the surface, more than an hour in the rest of the universe. Time is not a constant background against which events occur. It is a local property of spacetime that varies with the mass and motion of the matter around you. There is a region of spacetime around a rotating black hole called the ergosphere that deserves specific attention. The ergosphere is not inside the event horizon, it is outside it, a region of space surrounding the outer event horizon where the rotation of the black hole is so extreme that spacetime itself is dragged around with the rotation. This effect is called frame dragging, a prediction of general relativity that has been confirmed by measurements of gyroscopes in Earth orbit by the Gravity Probe B satellite. Near Earth, frame dragging is tiny, measurable only by extraordinarily precise instruments, irrelevant to any ordinary process. Near a rotating black hole, frame dragging is total. Inside the ergosphere, the dragging of spacetime by the black hole's rotation is so extreme that it is impossible to remain stationary relative to the distant stars. All objects, regardless of how much thrust they apply, are dragged around the black hole with the rotation. Staying still is not an option. The rotation of spacetime itself carries everything with it. In the ergosphere, the temporal dimension, the direction of increasing time, has been tilted by the rotation until it partially overlaps with the spatial direction around the black hole. Time is not running backwards, but time is running in a direction that is partly sideways. This is the region where a process called the Penrose process can occur, an object entering the ergosphere, splitting into 2 parts, and one part falling across the event horizon, and the other escaping with more energy than the original object had. The extra energy comes from the rotational energy of the black hole itself, extracted by the geometry of the ergosphere, energy extracted from the rotation of spacetime, from the place where time runs sideways. Now take all of this, the swapped coordinates inside a Schwarzschild black hole, the closed time-like curves in the Kerr interior, the extreme time dilation near neutron stars, the tilted time of the ergosphere, and ask what it means collectively. It means that time, as a feature of the universe, is not uniform, not universal, not a background stage on which events occur the same way everywhere.
Time is a local property that bends, swaps with space, curves back on itself, and runs at different rates depending on the geometry of the space-time you occupy.
The universe does not have one time. It has a different local time at every point, determined by the distribution of mass and energy and the motion of the observer. The human experience of time, the sense of a single present moment moving forward at a constant rate into an open future, is a product of the specific gravitational and velocity conditions of life on Earth. It is not a fundamental truth about the universe. It is a local approximation that holds well in the narrow range of conditions that human beings have ever occupied. Elsewhere in the universe, time is doing things that our nervous systems have no category for. There is an experiment you can do right now. Take your phone out of your pocket, open the GPS application, watch it locate you to within a few meters. What is happening inside your phone is the reception and processing of signals from satellites orbiting 20,000 kilometers above you. Those satellites carry atomic clocks. Those clocks are corrected every day for two effects, one that makes them run fast relative to clocks on the ground because they are moving at orbital velocity, and one that makes them run slow relative to clocks on the ground because they are further from Earth's mass and experience less gravitational time dilation. The net effect is that without correction, the satellite clocks would drift by approximately 38 microseconds per day relative to ground clocks. 38 microseconds does not sound like much. At the speed of light, 38 microseconds corresponds to approximately 11 kilometers of error per day, accumulating. The GPS system would become useless within hours without relativistic corrections. You are using relativistic time dilation every time you navigate by GPS. You are relying on the correction for a universe where time runs differently in different places. The physics of bent time is not something that exists only in equations about black holes and neutron stars. It is in the device in your pocket. The universe does not ask your permission to be strange. It has already incorporated its strangeness into the infrastructure of your daily life. Here is what we know and what we do not know. We know that time runs differently in different gravitational fields and at different velocities. This is confirmed to extraordinary precision by multiple independent measurements across 7 decades of experimental physics. We know that inside a Schwarzschild black hole, the coordinate we call time swaps roles with the coordinate pointing toward the singularity. This is the mathematical consequence of the geometry, not an interpretation, not a metaphor, but a property of the solution to Einstein's equations. We know that the Kerr solution for a rotating black hole contains closed time-like curves in certain regions. We do not know whether these are real features of physical rotating black holes or artifacts of the idealized mathematical solution. We do not know what happens at the singularity. We do not know whether the chronology protection conjecture is correct. We do not know whether closed time-like curves are possible in physical spacetimes or whether quantum effects eliminate them. We do not have a complete theory of quantum gravity, the framework that would correctly describe physics in the regimes where both gravity and quantum mechanics are simultaneously important, which is exactly the regime of black hole interiors and singularities. Every human being who has ever lived has experienced time the same way. A single direction, past becoming present, becoming future, irreversible, inescapable, the same in every room of every house on every continent across every moment of human history. That experience is real. It is not an illusion. It accurately describes time in the gravitational and velocity conditions that human life has always occupied. But it is not the only way time can behave in the universe. 60,000 light-years away, at the center of our galaxy, Sagittarius A star, a black hole 4 million times the mass of our Sun, rotates. Around it, the ergosphere drags space-time with its rotation. Inside its event horizon, the coordinate we call time points inward. At its singularity, the equations stop working and no one knows what happens. There are billions of black holes in the Milky Way, supermassive black holes at the centers of 2 trillion galaxies, neutron stars scattered across every galaxy we have ever observed, all of them warping time, all of them creating regions where time behaves in ways that the experience of every human being who has ever lived gives no preparation for. The universe is not a place where time flows uniformly from a single past towards a single future. It is a place where time is a local property of curved spacetime, different here than there, different near mass than far from it, and in at least some places, structured in ways that no human being has ever experienced, and that our best mathematics describes only partially, and our physical intuition describes not at all. The single direction of time that feels like the most fundamental fact about existence is a local weather condition. Out there, the weather is different, and the forecast has no category for what it becomes.